week. All right. Hope everyone's having a good week. So, hope you had a good break, took a little time off, or and try to enjoy yourself a little bit. Weather's getting nicer. So tonight we're going to talk about. We're just going to wrap up linear regression, and I got a couple of things. I like to go through another example, one I kind of like a lot, and then I'm also going to talk about correlation a little bit more too. But before we get to that, I think we got a couple of presentations tonight, a couple of problems. So, Kyle, are you on? Let's see, I see you. All right, I can see your screen.
All right, can you hear me?
I can hear you.
Great. All right. Okay, so uh, my presentation will be about linear regression and murder. More specifically, it's about the relationship between the murder rate and the poverty rate. The following regression output is for predicting annual murders per million from the percentage living in poverty in a random sample of 20 metropolitan areas. And this is a five-part question. Let's get started with part A. Write out the linear model. The linear model is expressed as y equals beta 1 times x plus beta naught, where beta 1 is the slope of the line and beta naught is the line's y-intercept. From the estimate column of the regression output, we know that beta naught is equal to negative 29 and some change, and is the line's y-intercept. Beta 1 is equal to approximately 2.6 and is the slope of the line. Consequently, the linear model for the murder rate as a function of the poverty rate is expressed as murder hat equals approximately negative 30 plus 2.6 times the poverty rate. Before we continue, let's stop and check to the best of our ability, given that we only have the scatter plot and not the raw data, that the conditions for least squares regression have been met. Check the conditions. Linearity. The points in the plot do show a linear trend. Number two, nearly normal residuals. From the scatter plot, we don't see any outlying points. Number three, homoscedasticity, aka constant variability. Having only the scatter plot, the points appear to have constant variability. And lastly, independent observations. The data are from a random sample, and they are not from a time series. Part B, interpret the intercept. The expected annual murders per million in metropolitan areas with no poverty is approximately negative 29.9. However, since this is not a meaningful value, it merely serves to adjust the height of the regression line. Part C, interpret the slope. Since beta 1 is positive, we should expect a positive relationship between the variables. For each additional 1% increase in the poverty rate, we would expect the annual murders per million to increase on average by 2.6. As always, we should remember that correlation is not causation. Part D, interpret R squared. In our model, R squared is 70.52%, which means that the model's least squares line accounts for approximately 71% of the variation in the annual murders per million. And finally, part E, calculate the correlation coefficient. Well, we've been given R squared in the regression output, so we would just take the square root of R squared, and we would get that R is approximately 0.84. The end.
Thank you very much, Kyle. Um, is it Isla? Is it
Ilya, close enough.
Ilya? Okay, Ilya. Sorry about that.
Uh, I've heard worse.
All right, there we go. We can see your screen. We can hear you. It's all yours.
All right. Actually, all the assigned practice exercises were taken from Chapter 7, so I just picked another one, and my presentation is probably going to be very similar to Kyle's. I picked problem 35, deals with the relationship between the weight and the height. And they give you the scatter plot and the summary table. So part A is the relationship, and just based on the scatter plot, it does appear to be linear. It's definitely a positive, and it kind of seems like there's a moderate, maybe it's a strong relationship between the height and the weight. The equation of the regression line based on the summary table, we can just take the values for the slope and the intercept, and you see the equation on the screen. The slope essentially means that for every additional centimeter in height, the weight increases by a little over 1 kilogram. And the intercept is that for a height of 0 centimeters, the average weight is minus 105, which is obviously not realistic. So that's just to describe the regression line. Whether there's a strong evidence, the null hypothesis would be that the beta 1 is equal to 0. So the slope is 0. Essentially, the regression line is just horizontal. And the alternative hypothesis would be beta 1 is greater than 0. When we look at the summary table, we can see that the value of the summary table actually lists as 0, so it's probably very close to 0, and that's for a two-sided test. So for a one-sided test, that's going to be even closer to 0. So we definitely reject the null hypothesis, and there's probably strong evidence that increase in height leads to increase in weight. The correlation is given as 0.72. They ask to calculate R squared, which essentially just square the correlation, comes up to 0.5184, which is just under 52% of the variation in weight can be explained by the height. And that's it.
Thank you very much. And last but not least, Michael, are you up? There, I see you. There you go. You there, Michael? Your microphone screen.
Hello?
Oh, there we go.
You can hear me now?
Can hear you great. Can see you to
All
your
right.
screen now.
Oh, all right then. All right, so 7.39 urban homeowners. So exercise 7.33 gives us a scatter plot displaying the relationship between the percent of families that own their home and the percent of the population living in urban areas. Below is a similar scatter plot excluding District of Columbia, as we know, as well as the residuals plot. There are 51 cases. You can see every little case right there. And here are both the graphs provided. Here we go. A, for these data, R squared equals 0.28. What is the correlation? How can you tell if it's positive or negative? So I made a little graph here of a bunch of graphs, a graph of a bunch of graphs. We have this line going down. I'm not sure if you see my cursor, but this one goes down fitting our correlation to 0.52, which is between low negative correlation and high negative correlation. How can we tell if it's positive or negative? That's if it's going down or up, left or right. And what the 0.28 would mean in terms of correlation, the R squared, is 28% of the variability in the percent who own home is explained by the model. The B question, examine the residual plot. What do you observe? Is a simple least squares fit appropriate for these data? There are 3 requirements for it. There's linearity, nearly normal residuals, and 3, constant variability. So I believe this is quite linear in that it is going in one direction. we have two nearly normal residuals? I would say no, because I drew a line in between the plot vertically, and I see that the right is much bigger than the left, and that would not be a normal distribution. 3, constant variability. We can check that with these two rays, one going up here, one going down here. No, it is not a constant variability. You see as it goes farther to the right, the variability gets higher, as represented by my mouse going up and down. All right, that is my presentation.
All right, thank you very much, Michael. That was good.
Nice.
One other thing I'd just point out on the question that you could have said for the R squared is you can't tell if the correlation is positive or negative with only the R squared. You actually need the visualization, because once you square it, you lose the negative sign. So another way of thinking about it.
Sorry, I also square rooted it. I left that out. I'm sorry.
Yeah, well that's fine, but you can't take a square root of a negative number, or I mean, you get an imaginary number, but in the statistics world, that's not terribly useful. So the R squared is always going to be positive, right? Correlation could go from -1 to 1, but R squared always goes from 0 to 1.
Ooh. Thanks for pointing that out.
Yeah. So yeah, that's when we do a lot of stuff like ordinary least squares, one of the remember, actually I'll talk about that again when I show the example. I'll try to remember to point it out, but when we look at the residuals, we actually square the residuals, and one of the reasons, there's two reasons why we square the residuals. One is it makes all of the differences positive, so when we sum of it up. So otherwise we could, a couple of things could end up happening if you have both negative and positive, but we just want to take all errors the same error, whether it's positive or negative. So that, we could do the absolute value, but the second reason why we want to square it is it sort of penalizes data points that have larger residuals. So the relationship's not simply linear, but the further you go away, the larger that point's going to contribute to the error term in the sum of the squares, which is why we remember. And actually, if you look at the 2 weeks ago slide, particularly the points that we call leverage points, that are kind of fall far away from the other points. Reason why they impact the R squared so substantially is you think about the residual, which is you're going to take the distance from that point to your regression line and then square it, and that's gonna decrease the R squared because you're increasing the sums of squares. So we'll come back to that in a little bit when I go through the example. One other thing I want to point out, I'm not going to go spend a ton of time on this, but I wanted to point out this Shiny app that a friend and colleague of mine built for correlation. That kind of he presents correlation slightly differently. And when I talked about it, I defined it in terms of the sum of the products of the z-scores in the numerator. But there's another way that we can get to correlation, and that's through the sense of covariance. And he has some introduction here and kind of just provides a layout of he shows a bunch of, here's in the second row, perfect correlations, and then but obviously the slopes are different as you go through, and then here are some points where 0 being no correlation, with varying strengths of positive negative correlations here, but you could step through this little Shiny app, and so one of the points that you can make out, right? So you can simulate a bunch of data, and we can resample to get a bunch of them. You can change the correlation, but just for demonstration purposes, we'll keep the correlation pretty strong at a positive 0.8. And so this is just the distribution, and you can kind of play around with that. But then what you want to do is get in. So when we define covariance, right? So I'm not going to go through all of the details, but we have this parameter rho, which is the covariance of x and y, right? And what that's going to be defined as is the standard deviations of x, y, sort of a pooled standard deviation time divided by the product of the two standard deviations. And this is kind of gives us the covariance. So, but you can define the covariance this way, which I think is a little bit nicer for this purposes. And then we'll have a nice visualization where it's the sum of the, your data. So if you take for each data point that has an x and a y, we're going to subtract the mean, and then we're going to this mean of x, and then we're going to subtract the mean of y, right? And take the product of that and sum that across. So hopefully you see that. So if I start at this point, I'm going to take, in fact, what would be helpful is like if I show the mean of x. So I'm going to take this difference, right? And then I'm going to multiply it by this difference. I'm going to sum up that product, and I'm going to do that for every point and then divide by n minus 1. So what does that mean? So there's the deviation on the x, and here's the deviation in the y. So what you hopefully notice here is, okay, and if we're going to do this for all of these points, we end up with this rectangle. If we go to the next bit here, so if we have this cross product, so essentially the covariance is the sum of areas of going from that point to its corresponding mean. So the edges are the differences, right, from this point to the mean, and we could do this over and over, right? So we're going to sum all those and then divide by n minus 1. So when we get to the last one, so that defines the covariance. And so what it turns out is, from a visual perspective, is the covariance, the correlation tends to become a ratio of these pieces of the covariance. So here we could say, so here these blue boxes are all of the positive components in the covariance sum, right? So recall, this is our formula. So these are all the cases where the product here is going to be positive. But some of them are going to be negative, right? And which ones are going to be the negative are the ones that are in quadrants 2 and 4. Okay, so these are all these components of the covariance. So now we can look at all of them, right? And so what ends up happening is, well, we could look at a histogram. So we could see most of them are blue, right? If we go back to this picture, right, we see most are blue, but some are red, right? And then this is the histogram. We can I like this picture a lot. So we take all the squares from this frame and just pack them. So we can look at them on one plane. So in essence, what the correlation becomes is the ratio of the blue, the positive cross products, to the negative cross products. So in this case, this is hopefully from the basic scatter plot. You see, okay, it's positive, right? So it has this upper trend, but we can calculate the correlation from, oops, I want this one. Yeah, this one, right? As something, or as a ratio of these two cross product pieces of the covariance. So hopefully, go through this. He's got some text in here, and you can go through and reset it. So you can, if I go back, I think I have to go back to this one because he uses the same ones throughout, right? We can do the same thing from the negative side. And when we go down to here, I guess I got to do it here. I'm sorry. Right. So now we're going to have a negative correlation because we have more of the cross product pieces in quadrants 2 and 4, in the negative quadrants, if you will, right? And if we go and get it closer to balance, closer to 0, then we see, we have almost the same amount of red and blue boxes. That becomes particularly apparent when you pack them, right? Or if you want to look at the histogram of the frequencies of those. So anyways, I think this is kind of an interesting way, another way of kind of thinking about correlation as a decomposition of the covariance calculations. So take a look at that. All right, so of course, I wanted to talk a little bit more, revisit this correlation idea, right? Because that's really a key component, right? In the regression, right? In order to get the slope, we need the correlation. So I like this example a lot. If you grow up in New York, or if you have kids in New York State, or if you pay attention to education at all, some of you may know, right? Well, a couple of things is, if you have kids in New York, you recognize that from grades 4 to almost ever now, they're going to take some kind of high stakes assessment. And under the Bush administration, something that came out that was pushed nationally is this thing called Common Core standards. New York State adopted it, And then what was interesting is in 2013 was the first year that New York State used high stakes assessments, used high stakes assessments that were aligned to the Common Core. And if you follow the news, you might have noticed that in that year, it looked like all of the schools kind of dropped in score. And so one question is, what happened? Well, obviously the scores were, the tests were realigned, but was the drop really indication that students really knew less, or does it mean schools were doing bad? So one way to look at this is as a regression model. And so New York State makes this report card data publicly available. So here each row is going to be a school in the state. And here I'm just showing the first four. And so what we're going to want to look at, a couple of variables, is we're going to look at the pass rate for 2012 versus the pass rate in 2013. So these are, so we could see the average, for schools had an average passing rate of about 61%. And then the average passing rate in 2013 became 22.8%. So, this was an easy article to write in the New York Times for the reporters. Like, oh my God, the sky is falling. Students don't know anything. All right. So let's look at, we're going to do some descriptive statistics. We look at that. We see, okay, we could see not quite normally distributed. It looks like a little, skewed. And then we kind of reversed the skewness in 2013. So, of course, one thing, given that we have non-normal distributions, well, let's try a log transformation. We could still, it helps, but doesn't quite get rid of all of this. We still have a little bit of a tail here, but it's certainly one approach we could take. I'm going to come back, come back to the log transformations in a little bit. But for now, let's just look at the scatter plot. And here we see on the x-axis the passing rates for 2012 and the passing rates for 2013. So one question I had when I saw this data was, well, did the drops happen predictably? Because that could be indication of something. And then one of my research areas of interest is, this idea of charter schools versus traditional public schools. So, did the drop happen predictably for both public and charter schools, or were there differences? Now, looking at this, looks like it has a bit of a bend, but for teaching purposes, I'm going to just continue on as it's linear regression. And actually, I'll give you a quick sense of. I'll show you quickly how you can fit sort of a quadratic model here. Give me 1 second here. All right, so here's the log transformation. So this does a little bit better. We still so recognize what the log transformations are going to do on the 2013 is kind of, I only log transform the 1, so it doesn't really change anything in the 12. And the fact that we have perhaps a nonlinear relationship, we still see a little bit of bend. So we got a couple of options here. So remember, when we're doing linear regression, we want to look at the correlation and sorry. So first, we're going to look at the correlation. We see right away the correlation is pretty high. So even though we have perhaps some issues with it not being linear and some curvature and non-normal, the fact that we get such a strong correlation, with this kind of 95% confidence interval suggests that we can go on. So but we could see if I do the log transformation, which is going to help with all of my assumptions, my correlation actually gets a little bit stronger. So I'm not going to go through all the steps like I did 2 weeks ago. I'm going to go right to the LM function. And, we see that we have this model, right, accounts for, and here I'm not using the log transformations yet, right? So knowing 2012 passing rates explain 62% of the variance in the 2013 scores, which in the social sciences is a very, very large R squared. So, that's pretty interesting. But one of the things, and then if I look at the using the log transformations, I actually can get up to 70% of variance explained. So quite large. So a couple of points here is by realigning the test didn't really, I don't think, changed a whole lot of what we knew about students. Now, perhaps if I think the takeaway here is the tests were harder or didn't necessarily align to what was being taught in the schools because schools didn't have a ton of time to prepare. So to me, this is all very, very interesting when you can very accurately predict and understand the relationship between two things and kind of understand this phenomena. But something I was interested in and something that you might want to be thinking about is I wanted to know if the rates dropped in a predictable manner, in particular by this grouping variable I'm interested in charter schools. So we've been talking about residuals as really just in terms of evaluating the assumptions of the regression models, really for diagnostic purposes. But there are some situations where analyzing the residuals may provide some interesting information. So whether we do the log transformation or not, we had an R squared of at least 62%. So the question I had is, did the scores drop more for public schools than charter schools, or vice versa, or was there a difference? One of the criticisms and claims levied against charter schools often is that they tend to teach to the test and they do a lot of test prep. So a situation where if the test format changes from one year to the next, charter schools may fare worse than public schools, which are trying to just teach content from a more holistic or general point of view. In which case, the format of the test should be inconsequential to the assuming that the content is at the same grade level. So here, I can take the data and I can pull out the residuals from my linear regression. I'm just going to do it twice, and this is what I get. So this is the distribution of the residuals, and we see that the charter school, the traditional public schools is the red line, right? Kind of the distribution is slightly higher than that for the traditional public schools. There we go. And if I do look at the log the residuals from the log transformed data set, I see the same pattern. So I can go to our null hypothesis testing, kind of connect a couple of different ideas we've been talking about. So what I'm going to suggest here is if the scores drop predictably for public schools and charter schools, then the distribution or the mean of the residuals should be the same for both groups. And if they're not, then then there's a difference, and that could mean something in this particular case, that the predictability in the scores in 2013 from 2012 are not the same for the two groups. So you could do that. And so here I'm just doing a t-test on the residuals group against the charter schools, and in this particular instance, I end up with a statistically significant t statistic, and I have this is my confidence interval for my mean difference, for the difference in the means and the residuals. So what does this mean? So that means I'm 95% confident that the true mean difference in residual scores between charter schools and public schools is somewhere between 6.4 and just under 12. 12. So what's the scale here? Well, these are percentage points. So if whatever the drop is in the score between from 2012 to 2013, I'm expecting charter schools to drop 6.4 to somewhere between 6.4 and 12% more than a traditional public school. And so this kind of has some interesting implications. So Daniel, why did I do the t-test? And feel free to come off mute if you want to elaborate. So, You mean as opposed to just a simple null hypothesis test?
Or compared to another distribution.
Well, that's kind of what I'm doing here. I'm comparing the difference in. So it's I'm doing a independent sample t-test because I have two distributions. I have the distributions for charter schools, of residuals, right, and the distribution of residuals for the other group that I didn't say, traditional public schools, I think. So I have these two groups, and I want to know if the means of those two distributions is different. And that's what this confidence interval here is telling me, what the range of the differences of those two different distributions are.
Okay, thanks.
Does that help?
Yes.
If not, I can try to say it another way.
No, that was good. Thanks.
Okay. Yeah. So in this case, I wanted to know if two means are different, and that was the t-test. What I want to point out here is I'm looking at the means of the residuals, right? So kind of a step further. Now, there are a couple other things that, I could have done. I could have, fit two models, or in 2 weeks, I might show this. I have another example that I like better. I could have fit a multiple regression model, including the charter school indicator, the school type indicator, as another independent variable, and looked to whether or not that was a significant predictor, and looked at the slope for that second variable. But this is, to me, a little bit of an easier way, from my point of view, to explain it, because really what I want to know is, did the predictability differ for these two groups under this single linear model? So I can do the same thing. This one's a little bit harder to interpret. So I like this one because I can interpret this as percentages, right? Because that's the scale of the residuals of my y-axis, where now it's the log of a percentage, and that becomes a little bit harder to interpret. But from another point of view is, I have a confidence interval that doesn't span 0, or I have a p-value greater than 0.05. So the means of the residuals are statistically significantly different, which is what I'm interested in. All right, so I mentioned this, right? We go back to that. If we look at this scatter plot, this one, right, we may see, hopefully you see, this doesn't look quite linear. So I'm doing something that may not be entirely correct, but I wanted to go through it and treat it as a linear model. Now, it turns out, if you see a bend like this, it's not terribly hard in R. It becomes incredibly hard to do by hand. So thank goodness for R, or Python, or other kinds of statistical languages. If there's a fit like that, well, I can just try to, instead of thinking of this as a linear equation, I can think of it as a quadratic equation, right? And so if you remember from high school algebra, right, by squaring this term, I'm actually going to end up with the parabola, but I'm going to restrict it to where my data points are. And I can do this using the same LM function. The only thing I'm doing here is I'm squaring this term, and I have to add this I here, and I always forget what I think it stands for. Identity. It's just an indicator to R to tell it to treat this variable a little bit differently. And so you can see, if I fit this now, a quadratic model, I have an R squared of almost 70%, which is, let me see. So this is the quadratic, right? And remember what my linear one was 62%, right? Because I think, and then I have a picture here, right? And why is that? Why was the R squared better? Well, remember, what the R squared is related to is going to be related to the sum of the square of the residuals. So in the case of the linear model, actually, I'll show one in a little bit, right? This line is going down. I'm going to my residuals are going to be larger, but by kind of fitting to the bend of the data, right, the distance from all the points to this line are going to be less, which is going to mean the residuals are less, which is also going to mean my R squared is going to be less. And we can kind of get all this out. Now, a couple of things that are going to be a little bit different, right? So we can't interpret this estimate here necessarily as a slope in the same way, because it's not a, we still have a change in y over change of x, but now we have this square term. So it becomes a little bit harder to kind of do that, because the rate of increase is going to be larger, and actually over here the rate of increase is 0, right? And then it's going to be negative, right? So that's kind of a nice thing that you can do with the quadratic if you find yourself with a data set like this. If you want to play with this a lot more, let me pull this up. I'm going to switch over to our studio. So all the code for this is something I wrote a while back. It's all on GitHub at that link. Give me one moment. It's downloading from GitHub. There we go. Let me resize this. All right. So what's kind of nice about this is, so you have ELA in math. And we have grades 3 through 8. So if you want to explore other data sets, I think this is the one I was looking at, math 4 through 8. And so I just kind of changed this so I can look at it if I want to. So this shows the linear fit, right? And so think about when we look at the r squared here. So under the r squared, under this one of 68%, when I go to the quadratic, I go up to 74%. And why is that? Right? And is to get that r squared is I'm looking at the residuals here, right? And so I have let's look at this point, right? So this blue point, that's the residual. When I go to the quadratic, or if I picked that one, maybe it would have been better, right? It's much smaller, and on average across all the points is going to be much smaller that way. Now, if I go through different data sets, not all of them are going to be, this one might be reasonably linear. So different grade levels were, kind of had different behaviors, but it's not terribly difficult in R to consider these other ones. If you're so interested in Shiny, which I think is a great way of displaying results, you can look at the code, because this is a pretty simple example where I'm just kind of going through different ones and a couple of other things we can do. So I live in Albany County, so I can look at, well, what are the schools? I can subset the data points to schools in my county. And you maybe, if you're in Brooklyn, right? So you can look at the Brooklyn schools. But from my point of view, who has done a lot of charter school research, to me, what became interesting is the fact that most of these charter schools fell below these regression lines. So anyways, this is kind of a nice to present this as another way of thinking about regression as you get into a data science point of view. Sometimes examining the residuals for more information than just diagnostics could be useful. Oops, let's not show my email, and I went to the wrong screen. So are there any questions about this? So I think that's my last slide. So you get 2 Shiny apps to explore, this correlation one and then this little school one. Any questions about the final project? I think I graded all the people who resubmitted their proposals. You should have grades in there now. How's that coming along? Any questions on that? Oh, let me see. I can unmute everyone if you want to just speak up. Oh, the
final project is due in May 18th. May 8th.
Sounds about right. Let's take a look. Yeah, May 18th, I think is. Did I put it on this page explicitly? Oh, I hit the wrong one. Project. I think it's May. Oh, it probably says in Blackboard. Oh, but I usually have it due when the final exam comes out. Oh, Kyle, you're breaking up. Interesting. Ooh. Who's asking a question? Oh shoot! I put that.
Yeah, it does say on Blackboard the 18th.
Okay, thank you, whoever looked at. I'm gonna mute. If you, any other questions? Oh, oh no. So Chris. All right. Is it breaking up on my end or on everyone's end?
Everyone's.
So am I breaking up to you?
No.
Oh.
Just Kyle G.
Sorry, Kyle. Okay, great. That was weird. Okay, good. Thank you. So no, the final exam is different. So I haven't finalized the final exam. The way I write it as if it. I tend to do final exams with the idea that it's something you could do in one sitting. So historically, I try to keep it to about a 2-hour activity. And I usually split the final exam kind of into two components. One is you're going to do some more writing, kind of addressing some conceptual things that we've talked about this semester. So key concepts like what the central limit theorem is, how do you interpret a p-value, some things regarding regression would be good. Some things about visualizations, knowing, what's appropriate at different times is good. And then I usually have a short activity where I'll give you a little data set to do some stuff with. No, I don't provide a study guide because you can use your notes in the book. It's I would use whatever materials you have, so that'll be your study guide. Not timed. Well, timed insofar as my schedule. I think I gave you a week, but my expectation is if it it should take a median amount of time of 2 hours. Some of you could probably get through it quicker. Some of you will take a little bit more time. Other questions? Open intro. Yeah, I mean that book that's sort of the book of record. Can I send your friend's Shiny app link? You mean, oh, can you share the link? Of course. That's a question.
No, what I meant is from the beginning you showed some Shiny app from I don't remember what.
Oh, Michael just put it in for you. This one. This is the one you want? My friends, yeah.
Yes, thank you.
Yeah, Michael beat me to it. Any other questions? All right, so I think we have 2 meetups left. So we won't have a meetup next week because I'll be on a plane at this time. But I'll be around. So if you have questions, then we're going to do multiple logistic regression in 2 weeks. That'll be. I think what I'm going to do is make this the last chapter because looking at the calendar, so that'll be you'll have multiple logistic regression due around May 7th. Then we're going to talk about Bayesian as sort of the last lecture because I feel like it's good to introduce it. I think on the homepage syllabus, I link to a chapter that's pretty good. I'll also give you some other references, but there will not be a homework or a lab on Bayesian analysis. So it'll be a read and attend the meetup, and I'll give you sort of a very high level introduction of what Bayesian analysis is about. And hopefully that serves you well as you go into other classes. Unfortunately, I don't think this program really has a dedicated Bayesian course, but you're gonna touch upon it from time to time, particularly as you get into machine learning, because some of the Bayesian models are really the ones that are performing quite well. Or if you get into some of these things like superlearner or ensembles of ensembles, but they often include Bayesian. No, Pavan, you're going to take the final exam at home. Sort of an honor policy that you guys won't share answers or communicate with one another. So typically, I'll make the final exam available by around midnight, so you have it on the 19th. So, look at it and schedule yourself accordingly. All right, well, from home or Starbucks or wherever you like to work. All right, well, if there are no other questions, we can end a few minutes early. Hope everyone has a fantastic weekend. Take care.